Okay, now let's look at the code. I used the MATLAB to do the code to design the whole programs. The whole iris recognition system is composed of three separate uh, programs. They have different functions, and there are also some sub functions, sub programs in the system. So the three separate programs, they have GUI. You can see from here, and they called the other sub function, sub program to realize the desired function. First, let's look at some sub programs. The first one I want to introduce is the draw circle. This program is to draw a circle in the picture to locate the iris and the pupil area. The program includes a function to generate the pixels on the boundary of a regular polygon of n size. So it doesn't indeed draw a circle. It just draw a polygon which approximate the circle. You can see that the input parameter include the image, the center coordinate of the image, the radius, and the number of sides, and its output the its output image with the circle. Then the next one we look at is the generate templates function. This function is used to generate a template of picture. It's very simple and basic. Then the next one is the getRing function. You can see this function is very like the first one. It's just to cut the iris ring from the localized image. You can see the input. You can see the input parameter includes the image, the iris center coordinate, the pupil center coordinate, the radius of iris, the radius of pupil, and the number of sides. And we need to pay attention that the origin of coordinates is at the top left corner, and the positive x axis points vertically, and the positive y axis horizontally, and to the right, the positive x to the downside. So the output is an image with circle. And then the Hamming dist function. This one is very simple function to calculate the Hamming dist. The input are two images, image 1 and image 2. The output is the Hamming distance. And then the lineInt function. This program includes the function to calculate the normalized line integral around a circular contour. A polygon of large number of sides approximates a circle, and hence it is used to calculate the line integral by summations. So you can see the input includes the image, the central coordinate, the radius, the number of sides, and then the last one we need to pay attention. The part is used to indicate whether they search it for an iris or a pupil. If the search is for the pupil, the function uses the entire circle for computing. The output is L, which is the line integral divided by circumferences. Then we need to focus on this function. This is the function which realized my improved method. You can see the input parameter is the image and a parameter. We use this scale to calculate the number of pixels we choose as a group. Then we choose the group each time in the whole image matrix and go through the whole matrix, and we keep the darkest part. And then we use this part as the center to cut off a square which with size equals to 150. You can see 75 is half part of the side, so the whole length of the side is 150. Then we do the exchange because we need to keep that uy is always a smaller coordinate, ly is always a larger coordinate, ux is always a smaller coordinate, and the lx is always a larger coordinate. So this function realizes this method. It's very simple, but it's quite useful, and we will see the results later in our program. Then this one is the this one is the normalized function. This function is used to perform normalization of the erased region by unwrapping the circular region into a rectangular block of constant dimensions. It's not very hard to understand. You can see there are many input parameters: the image, the x coordinate of the irish, and the y coordinate of the irish, the radius of the irish, and the same to the pupils, and then the image function file name, and then the last two ones, the red pixels, it stores the radial resolution, defines the vertical dimension of normalized representation. Then the angular dial is used to store the angular resolution, defines the horizontal dimension of normalized representation. And then the partial function. The partial is a combine of the meaning partial derivative. This function is used to find the partial derivative. We first calculate the partial derivative of the normalized line integral, holding the center coordinates constant, and then smooth it by a Gaussian of appropriate sigma. You can see the input parameters included the image, the center coordinates, the max and the minimum radius values, and the number of size, and the part is used to specify whether it is searching for the irish or pupil, and we need to pay attention to the sigma. Here it is used to store the standard deviation of the Gaussian. The output includes three parameters. The B is the max value of blur, and blur is just the finite differences vector, and R is the radius at maximum value of blur. Then the search function. This one is very simple. It's used to detect the pupil boundary. It searches a certain subset of the image with a given radius range. You can see the Rmin and the Rmax. This determine the radius range. It's use this to search around 10 times 10 neighborhood points. And it returns the central coordinate of pupils. Then the last one is the thresh function. This is a little complicated, but it's just a function to realize the famous Kramers and Wales algorithm to search to locate the iris in the pupil area. It is used to search for the central coordinates of the pupil and the iris along with their iris radius. It's just make use of the Kramers-Welles method to select a possible central coordinate first. Then this method consists of thresholding followed by checking if the selected points are correspond to a local minimum in their immediate neighborhood. These points serve as the possible central coordinates for the iris. Once the iris has been detected, the pupil's central coordinates are found by searching a 10 times 10 neighborhood around the iris center and varying the radius until the maximum radius is found. Then you can see the input parameter include the image, the mean radius and max radius, which determine the range, and then the output include the central coordinate of iris, the central coordinate of pupils, and the output segmented image, which is represented out. Pay attention here. We use this function to do this, and we will get the time required in the whole algorithm. So all these above are the function sub-programs. Then we will see the main three programs which has their GUI and has serve as the specified function. First one is the localization system. This is very simple. We can see that there is a specified GUI and several buttons, and it was clear and easy to manipulate. First, we load a picture. Let's load this one. You can see it appears here, and we can load new picture, or you can also reset the picture. Then we do the Kramers and Welles method to locate the area. You can see that it's declared in a right circle, and the time is also shown here. And then we do the localization, which come out with the close-up of picture. And we also use the Kramers and Welles method to search this picture, and then we use the white circle to determine the boundary. And then we add 2 times in the second algorithm together. We find that even though we add 2 times, it is smaller than the first one. So the second method is faster than the first one. And then the next one is iris system function. The iris recognition system. This one is a simple iris recognition system, which also has another GUI. First, we load an image. This time, we load another one. You can see we load a picture which is different from that one. It has a rotation in the eye. And then 3 buttons appears. First, we detect the iris. It's just use my method. You can see it's very fast. And then we normalize this iris and generate the template. You can see that this method can also work with the picture which has a rotation. Then the last one, this one is the iris compare system. It also has another GUI. You can see 2 buttons. The first one, we load a picture. Let's load picture, this picture one. And it generates a template automatically. Then we load another picture. We specifically choose another picture. If you look at it carefully, you can find that these are 2 pictures, but they come from the same eye. Then we compare. We can find that the Hamming distance between the template is smaller than 0.2. So this proves that the 2 pictures are from the same eye. So if we choose another picture, we choose this one. So these are come from the different eyes. Then we compare. We can find that the Hamming distance is larger than 0.2. So Consequently, the two pictures are not from the same eye. So all these are my erase recognition systems. Thank you.